Introduce Bijay. Bijay is currently an assistant professor at IISER Pune, which is the Indian Institute for Science Education and Research. Bijay obtained his PhD in 2013 from the National University of Singapore, and post that he first went to University of California in Irvine in Shaul Mukamil's group as a postdoc, and then later to Divira Sigal's group at the University of Toronto as a CQIQC postdoctoral fellow. Over the years, Bijay has earned a lot of awards, and I will just mention two, which are the most notable ones. The earliest one, I believe, was the Material Research Society of Singapore Medal for his PhD thesis. And then later on, for his postdoctoral work at the University of Toronto, he also won the CQIQC prize, basically. Over the years, Bijay has had a wide variety of research interest, ranging from quantum optics, quantum thermodynamics, and in general, various aspects of non-equilibrium statistical physics. With that, I would like to welcome Bijay, and today he will talk about thermodynamic uncertainty relations in quantum transport, giving us both a theory and an experimental point of view. With that, Bijay, the stage is all yours.
All right, thank you. Thank you so much, user, for the kind invitation as well as nice introduction. I hope all of you can hear me clearly. First of all, I would like to thank all of you for joining in. So today what I'm going to talk about is some of our recent research. In fact, for the past 2 years, one of the research direction that we are focusing in, which is called this so-called thermodynamic uncertainty relations. So this relation was given in different type of for different type of systems, but we will be particularly looking at in the area of quantum transport. So I'll give you. I'm a theoretician, so I'll certainly stick to most part of the talk will be more of a theoretical understanding to these relations, but I'll also try to give you some flavors of our collaborative work with other experimental groups. So I should first thank to all the collaborators, which are some research groups from IISER Pune, as well as my PhD students and undergraduate student. I have to thank Divira, where this all started when I visited her in one of the summer. And of course, there is Oriental's group in Weizmann, with whom we also collaborated to sort of understand the experimental aspect of this uncertainty relation. So I might just use a short form of this thermodynamic uncertainty relation in this talk, and I'll probably call it TUR, T-U-R. I'll call it TUR. And these are some of the references from our group where these papers are essentially focused on this work. And yeah, so I'll be mostly focusing on some of these papers, maybe not all, and feel free to take a look. And certainly if you have any questions, please stop me during the talk, as well as after the talk. I'm more than happy to discuss with you. So before I begin, I mean, since it's an international audience and some of you may not be aware of where I'm located, so I'm just going to present one slide about the institute where I am. So our institute is known as IISER, which stands for Indian Institute of Science, Education and Research. So this institute was established in 2006. And just like IIT, I think most of you are familiar with IITs, which are called Indian Institute of Technology, which have branches all over India. IISER also have now 7 different institutes all across India. So I'm right here, I'm located here, and I'm spending time here since 2017. So this is quite a beautiful green campus that we have. And at the center that you see is our famous cricket stadium. I believe many of you know that we love cricket, and there is a wonderful cricket league going on right now. So we, of course, live in campus. The students and faculties, everyone leaves campus. This is the main building where we have most of our research. You could probably see a building called H Cross, where we have also a lot of experimental facilities. This small building where we have all the undergraduate lectures. So this institute, we have all the undergraduates in all different disciplines of science, as well as PhD and postdoc programs. So in total, around 1,500 people live within the campus. So, and this is also in the heart of the city. So if you visit us, certainly there are a lot of places where you can go and have fun. And certainly, I believe some of you might heard of the place called Goa, which is very close to this beach, this seaside. And certainly, if you visit us, I can promise that I'll take you there to have some fun. All right, so this is one slide about the geography. With that, let me try to begin. But before, in fact, getting into the thermodynamic uncertainty relation, let me tell you what kind of problems that we are largely interested in. So this will be also important to really get into the idea of this tour. So largely our group is focusing on understanding non-equilibrium systems and primarily quantum systems. So the kind of design we have in mind is that you have a system of interest which could have many discrete levels. They could be small or large, but generally quantum, that's where we are interested. And the system is not isolated, but it interacts with multiple baths. Okay, and these baths in principle can be bosonic or fermionic. They could be at different temperatures, chemical potentials, and that essentially will drive current through the system. The system in general can have many types of many body interactions, electron-electron, electron-phonon, and so on and so forth. Given that we are interested for this generic type of system, various type of fundamental as well as practical questions. So at the fundamental level, certainly what you can ask is that how, for example, the system behaves as you look at it as a function of time. For example, you look at currents and how it essentially reaches a steady state. So you can look at quantum dynamics. You can as well, once you reach steady state, you can look at what kind of signal, what kind of information you get by looking at the current as a function of various tunable parameters. One of the other direction that we work on is this quantum thermodynamics, where essentially the whole idea is that you take into account all possible sources of quantumness and try to build up the laws of thermodynamics. So that's another aspect. Another major sort of goal and focus in our group is, if this system of interest is small in size, then as we know from our statistical mechanics idea, that there could be large relative fluctuations, which cannot possibly be ignored. And then the mean that we are typically interested in, the average, that's not really the only quantity to look at. And you probably should start going beyond that and look at noise and the question, or fluctuations. And the idea is that what information you get from these fluctuations. And people have looked at this fluctuation, and this is still an ongoing research direction, where these fluctuations turns out not to be arbitrary, rather they follow certain universal relations, and they are known as fluctuation relations. So I'll spend a little bit of time on that. So these are kind of fundamental side of questions that we ask for these systems. And at the practical level, since there are multiple currents that are flowing through the system, you can certainly talk about different types of quantum devices. For example, you can talk about diode. You can talk about so the basic question is, how can you engineer this kind of systems, or how you can tune these systems to obtain certain type of functionality. For example, you want to realize diode. What should you do? You want to enhance efficiency of this type of systems. For example, you want to realize this as a thermoelectric system or some kind of heat engine. How do you optimize? So what kind of quantum effects that you should have to enhance the efficiency and power output for these devices. So these are at the level of practical questions. So since I'm a theoretician, the kind of quantities that we are interested in, of course, one of the quantity is the reduced density matrix of the system. Remember, this is open, so the density matrix is the framework that you should look at. Of course, there are multiple types of current. There could be particle current, there are energy current, there could be current flowing due to electrons, phonons, and so on and so forth. And there are current correlations. As I said, there are these fluctuations that could be important. So you can as well start looking at those, and also efficiency. So these are the kind of things, basic things that we look at. At the level of tools that we use to solve these kind of non-equilibrium problems, so one of the famous approach is this Keldysh NEGF, non-equilibrium Green's function, that we use. We also have a quantum master equation approach that we use often, as well as certain type of path integral tools. So one of the review article that we wrote at the time, Juzer is also one of the author in this paper way back in PhD time in 2014. So with that, let me now take you to the plan of my talk. So what I'll begin with is to give you a brief introduction to the so-called fluctuation relation that I briefly talked about in my previous slide. And then I'll get into this sort of new kind of direction or new kind of problems that people are looking at is a so-called thermodynamic uncertainty relation. So here I'll spend more time in terms of theory, and then I'll take you two examples. And unfortunately, I won't be spending much time on this particular problem, but I'll just flash the result. And then I'll tell you, so this is on the so-called steady state problem, and the other example is the transient problem. So these are the two that I'm going to mention for the experimental part, and then I'll try to summarize my talk. Okay, so what is the fluctuation relation? So I guess many of the many in the audience probably are aware of this, but before getting into that, in fact, let me briefly mention that what was known in the non-equilibrium physics for a very long time. What was known was the so-called the linear response theory. Okay, so by this sort of, but by linear response, we all understand what it essentially means. That again, let's say you have a system which is connected to, let's say, two electronic reservoirs, which for simplicity, let's assume they're at the same temperature, but the chemical potentials are different. So we certainly know from the second law of thermodynamics that on an average current will flow from high bias to low bias. But, and this bias difference could be arbitrary, right? So the V is the bias, which is the difference of the chemical potential. This could be arbitrary. But let's say you make this V to be small. All right, so that means you are close to equilibrium, and that's why it's like a linear response theory. Okay, so if your V is small, then there were certain well-established relations, universal relations that were known, I guess, since 1950 or even before that. And these are known, or summarized via certain names. They are called Onsager reciprocity relation. There is also well-known fluctuation dissipation relation, and these are valid again in the linear response. And what do I mean by that? For example, if you look at the steady state current, so this angular bracket J is the steady state current, and I can expand this current as a function of bias, right? So I'm expanding this as a function of bias. So certainly bias is zero, current is zero. And if you look at this, this is like kind of like the Ohm's law, right? So this is your linear response part, and this is what we call the far from equilibrium part. So you have the current, and this by double angular bracket, I mean is the variance of current. So this is the fluctuation, you can say, or the noise. And this noise will certainly have an equilibrium component. It cannot be zero, even in equilibrium. So it has an equilibrium component, and then you have out of equilibrium components, right? So in general, you can write these expressions. But as I said, in the linear response theory, you have these universal relations. And what it relation essentially tells you that if you have this kind of a situation, this S0, which is related to the fluctuation, gets connected to the conductance. This G1 is the conductance, right? And this is universal. This is no matter whether you have a classical or quantum system, this is turns out to be valid everywhere. Okay, so this is one form of the so-called Johnson-Nyquist theorem, and it's a well-known fact from a very, very long time. But then the question was, what happens if I drive the system away from linear response? Okay, are there universal relations? So that was one question that was there for the community to answer. And in fact, it turned out that there are universal relations beyond linear response. And in one of the contexts that is going to be important for this talk is since it's a charge transfer situation. So let's just quickly tell you what fluctuation relation means in the context of charge transport. So again, think of this system reservoir, you have current and you are in the steady state. Certainly current, if you think of it as a stochastic, it's a stochastic quantity. You have average, but you can as well talk about its higher order moments or cumulants. So in principle, you could have a distribution of current, right? But rather, it's not really the current that you look at. You start looking at integrated current, so which is nothing but the charge. So imagine the following: your system is in a steady state, and you're looking at how many electrons are flowing as a in certain time window. Let's say between 0 to 5 seconds, how many electrons are flowing, and this is a stochastic quantity. So you can construct a probability distribution. So what the fluctuation symmetry tells you is that the probability that electron flows from high bias to low bias, so let's say mu L is larger than mu R, so now it's a probabilistic statement, okay? So the probability that electron flows from high bias to low bias is exponentially larger. So take this log on the other side. If you do that, then it's exponentially larger because beta is inverse temperature, which is positive. And I said mu L is greater than mu R, this is positive. So probability of electron flowing from high bias to low bias is exponentially larger than probability of the reverse thing happening. All right. So this is turned out to be universal, but certainly under certain conditions. And I don't want to spend much time, but just to briefly mention this, two important conditions that comes in is that the reservoirs need to be distributed under certain grand canonical. So the reservoirs should be under grand canonical distribution with their respective temperature and chemical potential. So that is one crucial thing. And the second thing is the entire Hamiltonian that you write for the system bath as well as the system bath coupling, there has to be time reversal symmetry. So under these two assumption or these two conditions, you can prove these relations. But one of the wonderful thing is that this relation turned out to be universal, one, and second is this is valid for any arbitrary bias. Okay, so so it certainly goes beyond linear response. So this is true for any under those two assumptions, this relation is true for a wide regime. So certainly this relation.
I'm sorry, can you just remind again what P is? I probably lost.
What P? So the P is the probability of the charge in a given time window flowing. So plus N is the flowing from high bias to low bias.
Yes.
That's the P.
Well, again, it's a probability.
It's a probability, yes. Yes.
Of observing or finding what?
Probability of observing how many electrons in a given time window.
No, the probability is to observe, well, let's say what, n electrons?
N electrons, yes, n electrons.
Yes. The probability to observe n electrons doing what?
Flowing from, let's say, from left to the right.
During a given time?
In a given time window.
Okay. So you fix a time window and you ask, what's the probability that n electrons flow from left to right?
Yes.
And then in the denominator, you have the kind of reverse process.
Reverse process, right, right. And what I say is that, what this statement says is that they differ by exponential manner. So, so this might become clear towards also as I go along, and if not, then maybe we can again have the question.
And you say this is universal, so meaning that it doesn't depend on the smallness of the difference of the chemical potentials. Is that what you mean?
So when I say universal, okay, so this is a very interesting point. So you see this distribution itself, if you look at different system, of course, going to be different. But when you take this ratio, you see the right-hand side doesn't depend, the right-hand side completely depends on the affinities, right? It doesn't reveal any information about the system in general. So this is much like the detail balance that we have in equilibrium stat mech. Right? The ratio of the upward and downward rate follow, Boltzmann
Is
factor.
that therefore something maybe trivial, some people would say?
Well, in that sense, yes, you can say it's trivial, but that's going to be my next point, that you get something very, very general and very robust. And that's going to be the essence of this talk. So at this point, you are right. You can say this is trivial. What do I learn about the system? And you're absolutely right. You don't.
Yeah. And you mentioned time reversal symmetry. Why do you need that?
Okay, because you have this forward and so this forward and backward probability, these are the trajectory kind of notion that you get into the derivation. So that's why you need that property.
Okay, thank you.
Thanks. Yeah.
Bijay, there's another question.
Yeah, sure.
Alex, please go ahead.
Yeah, thanks. So actually, I have two questions. One is the continuation of the last question by Sergey. So you said you need time reversal invariance for this relation to hold, but from your explanation why you need that, it sounds, if you switch on the magnetic field, can you
yes.
Can you generalize it?
Yes. So it has been generalized even if you have magnetic field. So what will happen is that you, instead of the same P, you need some P tilde, and you have to reverse the magnetic field also. So if it is the, let's say there is a phi, so it's n phi and then minus n minus phi.
So basically, we need a generalized time reversal.
You can generalize it, yes. So people have done that. So I'm going to list the reviews article in the end of this slide, and yeah, you can find it there as well. But yes, you're right, absolutely. This can be generalized even in the context of magnetic field. Yes.
Yeah, thanks. And so the second question is perhaps trickier. So you were mentioning that the other requirement is basically that the reservoirs have grand canonical distribution.
That's right. That's right.
So I'm wondering what happens if you have systems. Basically, to me, a reservoir is just any system that's more or less at its stationary state and that's large enough so that you draw energy in the particles.
Absolutely.
But then, of course, I could try imagining systems that, well, perhaps something like an integrable system where you don't have just a simple grand canonical distribution, but something more complicated, or even Floquet-driven system.
Well, no, in that case, this relation will not hold. So again, that says, so we have to understand this. So you see, this probability are differing by exponential factor. Now, how this exponential factor gets into the theory? The reason being, the reservoirs are exponential, having this canonical or grand canonical kind of exponential factors. So if you deviate from that, if you don't make sure that, let's say the baths are driven and they are in some kind of a Floquet state, some stationary state, but let's say some Floquet state, you probably can write down, probably again, it's not 100% sure, some kind of an effective fluctuation relation. Sure, that probably you can do. But if I write down this, there is a absolutely strict condition that the reservoirs have. How you make sure that they are grand canonical is a different question, but you have to allow me to have this reservoir separately to be sitting in the grand canonical distribution at this temperature and this chemical potentials. If you change that, then this relation going to change.
Okay.
Yeah.
Thanks.
Yeah. For example, people have done a lot of work with squeezed path, for example, and this relation doesn't hold. I mean, maybe you can, in that case, define some effective temperature or effective, and then probably you can write in an equivalent form. So yeah, right. But at this point, let's just stick to this situation that the reservoirs are grand canonical, and under this you have this relation. So this is what we need. So as I said, that this is true for away from arbitrary, far from equilibrium. So certainly this relation should give us that what we know in the past, which is basically linear response results. So if I take somehow the limit close to equilibrium, I should get back what we have. But then that's not the only thing that we get back, as was mentioned, that this looks to be a very trivial relation. But actually, what you get back is something very, very general. And let me tell you that. So what we had before was, if you remember the previous slide, you have the current and fluctuation that you write in this form, right? But then, since I'm talking about the distribution, I can as well go ahead and look at other cumulants, the higher order cumulants, and I'm allowed to expand in this following manner. Okay. Now, what we knew, of course, in linear response is this: S0 coupled to G1. And that's universal. That comes from the fluctuation dissipation. But now from the fluctuation symmetry, you can actually show it's not only S0 that couples to G1, but in fact, these higher order coefficients, transport coefficients that you say, they also gets related. So for example, S1 gets related to G2, T0 gets related to R1, and in fact, it doesn't stop here. You in fact have infinite number of relations between these transport coefficients relating, for example, S2, G3, R2, and so on and so forth. And this is a consequence of this fluctuation symmetry. So this transport, so the relations between nonlinear coefficients is one of the outcome of this fluctuation symmetry. Okay, so this is one of the key thing that we need. And another thing that I want to mention, which is going to be crucial, is that for example, when you look at G1 in general is a positive quantity, is a conductance, right? But higher order transport coefficient, for example, G2, G3, they need not to be positive. There is no definite sign attached to these coefficients. We know, for example, if you look at noise, that's of course is a positive quantity because it's a variance. You can, since G1 is positive, you can show S0 is positive because they are related, but you cannot guarantee that S1, S2, S3, they all are positive. That's need not to be the case. Okay, so one of the questions that in general is, are there definite signatures or signs that you have for these coefficients? Something that I'm also myself don't know that if there are like works in that direction, but certainly these things can change sign, and I will show you what happens.
Sorry, Bijay, just a quick question here.
Yeah.
I was just wondering, you started the motivation by talking about systems that are small and hence fluctuations being important.
Right.
Is there some scaling of these coefficients with respect to system size that we know of? Because we would expect that these J2, J3 should go off to 0, right?
You're right. You're right. Okay. So that's a wonderful question. So certainly you can say that about the distribution. So typically what happens, we naively expect that if the system size is large, you get into central limit theorem and various such thing because of the system size, this distribution can become a very sharp. Okay, and what you can essentially land up getting, not if not always, you might approach towards a Gaussian kind of a distribution. So then what you just finally land up having just first and second cumulants, and these higher order fluctuations may not be that important. Sure, that surely can happen. Yeah.
Okay.
Yeah.
Perfect. Thank you.
Yeah. So here I've listed down this, my 3 favorite review articles in this direction, and feel free to look at. I mean, this is quite interesting set of results that you'll find in this. Okay. So given this, let me now get into the actual problem, is the so-called thermodynamic uncertainty relation. So what I'm going to focus on again in the steady state. Okay, and I'm also going to focus on two terminal situation. So I have some kind of a junction, some kind of a system, which could be finite, which could be large. We'll come back to that later. But then this system is coupled to two baths. And let's say they are at the same temperature, but the chemical potential is different. So then you have a current that is flowing and you're sitting in a steady state. So it's a situation which is a two terminal and a single affinity. So by single affinity, I mean, I just have a bias. I don't have any temperature difference. Otherwise, I could create two affinity problem. So I'm sticking to a simplest situation. So there was this bound that was given back in 2015. That was the first paper in this direction, which talks about certain bound. Now, bound on what? So this bound basically relates a relative uncertainty of the current. So if you look at just this first term, this is essentially noise over the current square. So this is like the relative uncertainty or relative uncertainty in the current. Now, so this is fluctuation and this is current. So this thermodynamic uncertainty relation essentially tells you that this relative uncertainty in current, you cannot minimize to an arbitrary precision. Okay, in a sense, there is a trade-off. And what is this trade-off? So it essentially tells you that in order to reduce this uncertainty, now this is something that we would love to do, we love to have, right? You want to have more current and less fluctuation. So you want to really have relative uncertainty to be less. So this is like attached to precision. So if you have this to be small, this is like the precision, right? So, but then there is a trade-off. So you cannot make this arbitrarily small, but in fact, it inversely goes with the entropy that you produced in this out of equilibrium system. So, and that is nothing but the cost that you pay. So this is, in that sense, is a trade-off relation that involves a precision and a cost, which is entropy production. Now, this has a lower bound that you have to spend at least something to reduce this relative fluctuation. Okay, and this, you see on the right-hand side, there is a 2. And the fact is, this was initially by Udo Seifert, this was given in PRL this paper, that this bound is greater than 2, but under certain condition. And one of the condition was that it's going to be followed for Markovian dynamics. So if the underlying dynamics for the system, if it is Markovian, then you're supposed to have this bound that involves relative fluctuation and entropy production. I'll mention what entropy production exactly mean, but bear with me. And so this is one of the form of the bound, and that's given the name of thermodynamic uncertainty relation. Now, what we'll see is,
sorry, Bijay, just a quick question. I mean, I believe this would also be only for weak coupling.
No.
But then what is the meaning of entropy production in strong coupling?
Okay, so this is a little...
Because you would need heat, right? I mean, you need entropy production will come from the second law, and you would need heat.
That's right. That you are right. Okay, so let me get to one example, and maybe I will try to answer there. Is that okay?
Okay, yeah, sure.
Okay, so just to be correct, I mean, this is entropy production rate. So this is not entropy production because we are talking in the steady state. This is entropy production rate. So there is this greater than equal to sign. There is this lower bound. Now, what you can show is that if by chance the distribution of current is Gaussian, which happens in the linear response, then you can show that this is exactly 2. Okay, so this is equal to 2. And the other thing that you can show is that if you take the equilibrium limit of this expression, you will also reach equality, and that essentially nothing but the standard fluctuation dissipation relation. Okay, but then that equality that you had in equilibrium, It's somehow when you drive the system away from equilibrium, it becomes a greater than symbol. Okay, so it becomes a lower bound. So that was the statement. But what we started asking was that how does this relation, how general or how universal this relation is if we go beyond. So the typical questions that we started asking is that does this bound, which I now call TUR, hold beyond Markovian limit, because that was one of the major limitation in this work. And the other interesting question that we started actually asking is that if this is universal, let's say for a second, then I know that there are this fluctuation symmetry, and the question is, if this is universal, then probably there is a way to prove this from the fluctuation symmetry.
Sorry, Bijay, there's a question from Alexei.
Yeah.
Yeah, sorry, I have perhaps a naive question.
Please go ahead.
You mentioned that this inequality, this bound is saturated for the Gaussian distribution of the current.
Right.
I wonder what happens for the Levy distributed currents and whether that's physical at all.
I cannot really answer. You're asking about Levy distribution, right?
Yeah. I mean, one particular example I have in mind is, of course, the one where you have the average, but the variance is not defined.
Very good. Yeah. Okay, Levy distribution clearly does that. Okay, in those contexts, you are. That's a very good question. If it is not defined, I'm not sure what would happen to this. So that's actually a fantastic question. In fact, I could add to this. I don't have an answer. I'm sorry about it. But one thing probably one should look at. I know, for example, there is this anomalous transport that happens in low-dimensional system where these processes are typically mimicked by Levy processes, Levy walks, instead of random walks. So it's a very good question, and unfortunately I don't have an answer, but something surely to look into.
Okay,
thanks. Sorry that I don't have the answer.
Bijay, sorry, one more thing. I'm a bit confused about, so you're always going to be talking about steady state processes.
Yeah, so I'm sitting in the steady state, right?
Right, and then what does it mean to be Markov or non-Markov?
Okay, that's another very good question. Okay, I'm going to answer that. Let me. So okay, probably you are aware that there are always a lot of fights about what you call Markovian dynamics and what you call non-Markovian. So here, if you look at this paper and the corresponding proof, this is what it goes. So you have the system coupled to bath, right? So you can write down. Let's say as long as you write down rate equation, Pauli type rate equation for your system, then and corresponding to that dynamics, whatever steady state you get, starting from Pauli type rate equation, whatever steady state you get, if you do that, with that restriction, if you do your analysis, this bound will be true. The moment you go beyond those traditional rate equations, this is what we are trying to kind of get into.
I see. But
so Markovian is essentially in this context is the Pauli type rate equation, or the equation that only involve populations.
I see. So there is perhaps nothing quantum then.
Kind of, you can say that. Yes. Yeah, this is a kind of a semi-classical, you can say. And in fact, our work was kind of, and you will see one example. Our work was trying to get beyond that. And we were trying to understand what happens to this. Exactly the question you're asking, like slightly going beyond semi-classical. It's what would be, does this get respected or is that gets violated? So that was kind of question. And in fact, that adds to, for example, the role of quantum effects. That's essentially what user is asking. Let's say I don't have only population, but I have population and coherence. What would happen? So this was the first work in this direction, which you'll find in this paper. But let me now try to show you what we have done. So just to give you reference, so this was the first paper by Barato and Seifert in this direction. This was the first PRL paper, and I guess by now there are probably 100 or 200 papers written in this direction. And it has really, this relation has been extended to various directions of statistical physics, many different areas. So okay, so we are going to understand this trade-off and how this is, whether this is respected or not. And for that, I once again need the idea of the fluctuation symmetry. So what we are going to do is that we are not going to ask what is the lowest bound. If there is a violation, what is the lowest bound? We are not going to really tackle that problem, but we are going to understand, can we sort of understand if there is a violation, how do we quantify that? Okay. So what we do is a very simple calculation. we essentially look at perturbatively what happens to this TUR ratio as a function of bias. Okay, so you have the current, you have the fluctuation, you have the third cumulant as a function of bias, right? Now, and we start from fluctuation symmetry because that was our motivation, that if it is at all connected to fluctuation symmetry, then it should be universal. So we use the fluctuation symmetry at the level of these transport coefficients, and there are infinite such, but we don't need, I think, more than this. And since we are focusing on this two-terminal setup, as I mentioned, the entropy production is nothing but the current times affinity. In this case, the current is the particle current that we are looking at, the charge current, and affinity is just simply V by T. The bias that creates the V by T is the affinity, and that creates the current in the system. So affinity is current times affinity. Current times the entropy production rate is the current times affinity. Now, very simply for this two-terminal, if you substitute your sigma here, one of the J gets cancelled, and what you get is simply this. So your 2 ratio is nothing but beta V times this. Now, the question is whether this quantity is greater than 2 or not. Okay, so that's the question. So what you do, in fact, what we have done is that you essentially take this expression for J and J squared. These are perturbative in the bias, and you essentially look at order by order in bias. Okay, now what very interestingly you see is that the first term 2 you get back. Okay, and that's precisely the equilibrium limit, and this 2 precisely comes because of this 2 that is here. Okay, so that's, as I mentioned, is a fluctuation dissipation relation. So interestingly, then what you see is that there is no linear in V term that appears. Now that is very interesting. The reason that this disappears is purely because of this relation, S1 equal to G2, KBT G2. And the other thing that yeah, please, Joseph.
Sorry, Bijay, there's a question by Igor.
Yeah.
Hello.
Yes,
so,
yeah.
Sorry for maybe an uneducated question. I don't quite understand why there are some non-zero entropy production rate in a steady state. Isn't steady state steady in the sense that it doesn't change?
No, because but you have your steady state is achieved through the baths, right? I mean, you have the system, which, so if you look at the rate of change of entropy of the system, that in the steady state is certainly 0. But then you have a current that is flowing in the system, right? So that generates entropy. So certainly, if you turn off your bias, there is no current that is flowing, and the entropy production rate would be 0. But entropy production is spontaneously getting generated because your system is away from equilibrium.
Could you please then define steady state here? What does it mean?
I define my steady state, for example, if I look at, if I give you this kind of setup, my steady state is essentially where constant current is flowing through this system. So whatever current comes out goes into this terminal. Let's say particle current. I'm looking at particle current.
But like in mathematical terms, in terms of, for example, the state of the system, the density matrix of the system, what is steady state?
Oh, state of the, in terms of, okay, so what you can think of, if you're aware of reduced density matrix, for example, you, for this kind of generic setup, you can write down, again, very nicely, let's say in the Markovian limit, a Lindblad kind of master equation, having 2 baths, and then your steady state is imposed by taking the limit time to be infinite, and it's essentially given by one of the eigenvalue of the Liouville.
Yeah, then I get a constant density matrix, and yes. Entropy constant density matrix cannot change.
No, but that's only for the system. You're not thinking about the bath. That's only for the system.
So that entropy production is production in the baths.
Yes, it's due to the baths, presence of the bath, because yeah.
Not due to the bath, but in the baths.
In the bath, yes, you can think. Yeah, yes, yeah, right. You're right.
So you are considering a non-stationary or non-steady baths.
My baths, individual baths, are sitting in equilibrium, but there is a non-equilibrium situation created because of this flow. Because these baths are at different chemical potentials, there is a flow, and that flow generates the entropy production.
Yeah, I see. Okay, thank you.
Oh, thanks you. Yeah. Okay, so what I was mentioning is that there is no linear term in the bias. And that is precisely because this relation, it disappears. And this is also kind of makes sense. Okay, I mean, one way to see is that if there was a linear dependence in bias, you could have easily violated this relation, because then all you have to do is to swap your baths. Okay, then V will become negative and you could easily terminate this, violate this. But that doesn't happen. It doesn't allow you to do that. But then the first non-trivial term that you get is V square. Okay, and then there are higher orders. So in this talk, we're just going to focus on this V square term, this up to this order. And what you see is that you have this particular C non-equilibrium, which I'm going to define, and then there is this G1. Now G1 is nothing but the conductance, so this is always positive, right? But then there is this guy C non-equilibrium, and that's what the key thing is. But let me now tell you, since there was a question about magnetic field. So if you now have magnetic field in this problem, and if you do the same calculation, you will see that order of V appears. Okay. So this is again because of this fluctuation relation and time reversal symmetry that this order of V doesn't appear in this expression. So your first non-zero contribution comes in V square. And the C non-equilibrium, you can very generally write, again, because we are doing quadratic expansion, in terms of these higher order coefficients. And it turns out miraculously, if you use again these relations between transport coefficients, you get C non-equilibrium is nothing but some R1 over 6. And now what is R1? R1 is apparently turns out to be the third cumulants, the linear coefficient of the third cumulant. Okay. So now, as I said, these coefficients need not to have definite sign. All right. So this guy, if this guy becomes negative, then at least in this order, you will start to see the violation. Okay, so that is the key. So, and another thing is that this result is valid, of course, since we are using only the fluctuation symmetry, which is valid for quantum or classical system. This is in general valid for general case.
Sorry, Bijay, just one more question here again.
Yeah.
The entropy production rate that you have here,
Right.
I'm a bit stuck on that, because this is again a result that you obtain when your heat current is nothing but your energy current in the absence of an explicit time-dependent drive. Okay.
Sorry,
so,
can you repeat again?
So if you do not have explicit time-dependent driving on your system,
right,
then whatever is your energy current flowing out of your bath, if you equate that to be your heat current,
right,
then this is what you will get as your entropy production rate.
right.
But then why is the heat the same as the energy current?
No, but hold on. I mean, all I'm considering here is the particle current. I mean, the baths are at the same temperature. So,
sure,
if you,
but there will still be a heat current in the
there
system.
will still be a heat current, but they will be decoupled. So,
yes.
So what? Yeah. So what? Okay, probably I should have been a little bit more elaborative here. So you see, so okay, so if you start defining the, let's say, the entropy of your system, let's say von Neumann entropy, and you take derivative, okay, the rate of change of entropy, you will see that there are two components. One, the two components which are essentially like entropy getting generated in the past, right? And this entropy is nothing but the heat, which is particle minus mu times the energy, right?
Yep.
If you look at the heat current, which is nothing but the particle times the mu times the energy current, right?
Yeah, but that's exactly where I'm coming from. That this.
Yeah, but remember that there is this. Of course, if the temperature is the same, I have the conservation of the energy current also. And if you manipulate there, you precisely get this expression. So
okay.
if your baths at the same temperature and different chemical potential, you can simply show. So just to give you, for example, if you have multiple affinity, your sigma you write as summation Fij, where Fi is the affinity that produces the flux times the Ji. Now there are two affinities, right? There are delta mu by T or V by T, and there is another affinity that will have 1 by T cold minus 1 by T hot times the energy current. But since the baths are the same temperature, that contribution becomes 0. So all you have is essentially a single affinity problem, and you have this to be your entropy production.
Okay. We can discuss this more. Yep.
Yeah, sure. Okay, so just focus on the C non-equilibrium, and if that becomes negative, then it's a violation of that relation. Now, getting into C non-equilibrium, of course, TUR, we are talking about current and fluctuation. Getting this is typically for interacting systems are non-trivial. So what we really first try to understand what happens for the non-interacting junction. So imagine you have a system coupled to bath, but the system is non-interacting. Okay, so this is for example, you have tight binding chain coupled to two fermionic Now, given this non-interacting problem, you can always solve this exactly, and this was done long back by Levitov and Lesovic. So what you get is for the current is a famous Landauer formula. Where you have T, this is the transmission, which essentially tells you, given an energy, what is the probability that electron flows from left to right. And these FL and FR are corresponding Fermi functions that are coming because of these baths. I have suppressed the index E, but they certainly depends on the energy, and you have the integral of it. So that's the famous Landau formula. And this is a transmission and Fermi function. And then, of course, you can as well write down the expression for the fluctuation. Now, one thing to note that the fluctuation not only depends on transmission, but it also depends on transmission square. And there is a negative sign, a crucial negative sign that pops out here. And this transmission square somehow sort of tells you, gives you information about the correlated processes, right, in the system. So you have this current and fluctuation. So you have everything, and you can investigate if there is a violation at all for the TUR. So if you take these expressions, you go ahead, do the calculation, and you get an expression for C non-equilibrium. Remember, that is what we are targeting. If this is less than 0, at least to this order, I have a violation. Now, what you find is that the C non-equilibrium has of this form. And once again, you have something which is linear in transmission and something which is quadratic in transmission, right? And this is coming because your noise depends on quadratic nature of transmission. Now, if this negative sign was not there, then we could have just closed everything, because then it's positive, okay? But because of this negative sign, you could have C non-equilibrium to be less than 0. And in fact, what you can argue is that you can switch the sign of this guy depending on the transmission, the structure of transmission. So remember again, because it's a non-interacting transport, a crucial role is played by the transmission function. So if you have different structure of the transmission function, which essentially depends on the system path coupling as well as the geometry of your system, you actually incorporate various type of tunneling processes. Your transmission function tells you underlying tunneling processes that are happening within the system. So depending on that, this gives you a signature, whether it could be positive or negative, as well as since there are Fermi functions floating around, there are these temperatures, if you can play with, you might start getting this to be less than 0. So certainly in a very general non-interacting setup, you can always plug in and start investigating, but then under certain limits, we could investigate and see that when this is always positive. So what we find is that if the transmission is low, so let's say this transmission is very, very small, then you always, at least to this order, your TUR is always valid. Low transmission, again, coming back to one of the question about Levy process, the low transmission sometimes often refers to a Poissonian process. It's kind of an uncorrelated transport process. And it turns out that here it's valid always. The TUR, the type bound is always valid. What we also found is that if the transmission is constant, then also this is valid. All right. But then there is a very wonderful limit, which often comes from the perspective of master equation, is the so-called resonant tunneling condition. So what is this condition? You see, you have your transmission function are often picked about resonant frequencies that you have in your system. But they are not delta peaks, they are broadened, and they are broadened by the hybridization due to the bath. Now, if you have a situation where your transmissions are sharply peaked, so that means your gamma is small. The gamma is the system bath coupling or the hybridization relative to the temperature. So in that situation, what you can have is that this transmission are sharply peaked and the Fermi functions are broad because you are in the high temperature. So then your main contributions to this quantity are coming only from those peaks. And you can then simplify this expression, and at the end, if you impose the condition that this has to be less than 0, what you get is this condition, that you can see violation to this order if the ratio of these two quantity, and they are nothing but the integral of transmission and transmission square. Okay, so if you happen to have this ratio to be greater than 2/3, you start to see a violation for the TUR. Okay, and that's essentially the resonant tunneling. So now let me now show you a couple of examples. So as it is a non-interacting, you can play with your system. You could have single dot, double dot, and it could have large system size. But let's just focus on the first two. So imagine your system just consists of one single dot or a double quantum dot. So again, these gammas are the tunneling weights, and this omega is the tunneling between the dots, and these epsilons are the site energies. So we all know roughly that if you have the single dot, the transmission is nothing but a pure Lorentzian in the weak coupling, right? And it's resonant, and it's a peaked about the dot energy, which in this case is taken to be 0. On the other hand, if you have double quantum dot, you basically follow this blue curve that you have two peaks at the resonant frequencies, and of course there is this broadenings, and that broadening happens because of these gammas, right? So this is in the weak coupling, because because you still see the peaks around the resonant frequency. But this structure of this transmission, as I said, this is the most important thing here. The structure of this transmission drastically changes if you take a strong coupling, right? If, for example, if you have a simple Lorentzian, if you take strong coupling, all you are doing is essentially broadening this peak more and more. So it kind of becomes flat, and you should follow this black curve. So transmission kind of becomes very close to 1. Okay. On the other hand, if you take a double dot and you make the coupling to be large, then what you can think of, if the coupling is larger than omega, you can think of this is separately in equilibrium with this is separately in equilibrium with this. So there is no current. So that means transmission is very small, and that's what happens here, right? In the very strong.
Bijay, we have
Yes.
a question by Alex, please.
Yeah, Alex, please go ahead.
Yeah, sorry. Would you mind going back to the previous slide?
This one?
Yeah, I was just wondering. So basically, get the negative C non-equilibrium is to have a strongly peaked transmission coefficient. I'm just
right.
Yeah, well, I mean, and additionally, this T2 over T1 greater than 2/3.
Right.
I'm just wondering, you could also just take the expression for the C non-equilibrium and see it as an optimization problem.
Oh, very good. Yes, right.
I'm wondering what's the best transmission coefficient? Is it just a collection of peaks? I mean, what is the most negative C neg that you can get?
Okay, that's a very good question. And once again, this is something that we are currently pursuing. So we are asking the following question. Since non-interacting system is purely described by transmission, what could be the shape of the transmission function that gives me the lowest possible value of TUR? And it turns out this resonant coupling, okay, we haven't have a conclusive result, but resonant coupling is a regime where you see actually the major violation. So that means you are right that this peaked structure of the transmission is what gives rise to violations. But again, that's not the only thing.
Yeah, I would even rather wonder, is it the best one? Can you still fine tune further to make the violation stronger?
I don't have an answer. That's a very good question. And we are currently, in fact, precisely what you said, we are currently really attacking the problem from the optimization. So at this point, this was not the thing that we started investigating. We were like, okay, where is the violation? Can we find some analytically some regions? And that's what precisely we have done here. But optimization is something that we are currently looking into.
Okay.
So yeah, that's a wonderful question, Alexei. Thanks for asking. Okay, so again, for weak to strong, the shape of the transmission changes, and that essentially tells you how electrons tunnel through the junction, and because of that, you could start seeing different. The bound could be different. To give you examples, so single dot. If you have a single dot coupled to two bars, you have the well-defined transmission. What you see is that here the violation only happens when your coupling becomes strong. Okay. If the coupling to the system between system bath becomes strong, that's the only regime where you see the C non-equilibrium becomes negative. So that's the regime where the bound becomes lower than 2. But of course, in this case, it's not a significant violation. I mean, it's still very close. It's kind of very robust. But here is one answer to that, this question, that why strong coupling? Because what you can show is that in the weak coupling, there is no violation. And the reason, again, from the master equation, if you look at the weak coupling, you have actually a population Markovian dynamics. And that's why the TUR, the tight bound, gets respected. But then when you go beyond weak coupling, you have or you go to the strong coupling, you have this multi-tunneling processes. You don't have single excitations because of weak coupling. And that's where you can start seeing the violation. So this is the strong coupling regime for single dot where you see the violation. But interestingly, when you get into the double dot, now that's where physics become little interesting. In fact, here is the weak coupling limit. In fact, already in the weak coupling limit, you see a regime where the violation happens. Okay, and in fact, this since this is a weak coupling, as I previously mentioned, that that's exactly what the resonant tunneling says. Is the weak coupling, your peaks are sharply peaked, and if you choose your temperature carefully, you can find a regime. And in fact, this exactly corroborates with the fact that whenever T2 by T1, remember that ratio, if it is greater than 2/3, is precisely the regime where you start to see violation. Now, one can ask why is a weak coupling, so there is a Markovian dynamics from the master equation, why there is a violation. Now, to answer that, you see where this violation happening. This violation happening for gamma of the order of omega, twice omega. So omega is 0.05. So if you look at 0.1, it's kind of the same order, twice omega. And that's the regime where actually population, if you write down the equation for the density matrix, you will start to see the population gets coupled to coherences. And that's why you get, so this is again, we didn't prove it, but this is an exercise that is going on right now, that it's precisely the one intuition that we have is that this regime, the population gets coupled to the coherence, and that leads to a kind of non-Markovian dynamics in the population space. And that's why it departs from what Udo's work in 2015, that where no, the population only following Markovian dynamics. So that's one way to understand. So there is definitely violation, and that's because you're going beyond the traditional Markov limit. And the other way to look at it is because you're looking at the ratio of the current and fluctuation, you essentially see the violation when you have more current and less fluctuation. So you see this is the regime where you have the violation, right? And that's the regime where current is more and simultaneously your noise is small, because you're looking at a ratio of noise over current. So this is another way to see it, but then this is not very important. So at the end, what we have is that depending on the structure of your junction, you could have violation, or and that essentially can tell you about the underlying processes. And what I mentioned is that if you have a single dot weak coupling, because you have a Markovian master equation, you have the TUR. But if you have in the strong coupling, you have higher order tunneling processes, so you don't have a Markovian master equation, and you could have a violation. On the other hand, for double dot, is the opposite, is the weak coupling where you have violation, but that's because your population gets coupled to coherences. And that's so because this is a pure exact analysis, so that's the way to look at it. Okay, so I guess I'm running extremely slow, but I think let's not rush too much, and I probably won't be able to cover experimental part. But I just want to ask user, how much time do I have?
Maybe another 5 to 10 minutes.
Okay, 5 to 10. So okay, so maybe okay, because there were quite few interesting questions, so it's fine. I mean, maybe we can talk about experimental part sometime later. But let's just get into slightly more into this. So since so far we have talked about charge transport, so we started now asking questions that what happens for the energy transport. That's another way, another type of transport that is quite interesting. For the electron, now think about you have only temperature difference, but no chemical potential difference. So again, a single affinity. So in this case, the entropy production is simply the affinity due to temperature difference, and this is essentially your energy current, right? So now this J is energy current, and once again you have the same formalism that you can apply. Note that I've changed the notation, unfortunately. So here I don't write double angular bracket, but I write a C. So this is nothing but the variance. So I have this, and once again you have a same form, at least to the order quadratic order of affinity, and you get this R1, which is essentially the the linear coefficient of the third cumulant, the skewness. So again, so I'm sorry, I changed the notation. So this R1 is like the C non-equilibrium. So if this is less than 0, you have the violation. So again, if you take a non-interacting junction, but now look at the energy transport, what you have, your things change slightly, because now to carry out the dimension of the energy, you have this this particular quantity, epsilon minus mu. And you can again do the same calculations once again, and what you can show is that you again have violations, and precisely around the same logic of gamma quite close to omega, you start to see violations. Now, and that again goes with the analysis that this ratio of the transmission greater than 2/3. But here your transmission definition changes a bit, because since you are talking here about the heat transport, so what you have is now you have E minus mu, this thing. And that essentially restricts the kind of transmission you have, because in order to have this analysis, your transmission should decay sufficiently fast so that you have this to be convergent. But one interesting point here to note that here, so that is the reason we have this results for triple or 3 or 4 quantum dots, because in that case your transmission typically decays as 1 over epsilon raised to twice n. So that's why they become convergent. You can do this analysis and you see the violation. Now, one interesting feature that we also see, and we ask this question, that how by increasing system size can you reduce it more and more? Because what is happening, this bound is coming because of the statistical fluctuation, the thermal fluctuation. You have the beta flowing around, but by increasing the system size, you also increasing more of quantum unitary processes, right? That is, coherent processes. So the question that we asked, that by increasing system size, can we lower the bound? And it turns out that no. I mean, after some value of n, it just saturates. And this is what you see, that there is not a significant difference if you have a triple or a 4 quantum dots. And this is a contour plot, which again kind of shows that you can get a regime, quite a broad regime where these violations could be significant. So this is for electron transport. This is the carriers are electrons. So it is a thermal transport example, but carriers are electrons. But what we on top of that, what we started asking is that how does, in the context of thermal transport, how does this too depends on the statistics of the carriers? Meaning, when I'm saying the statistics of the carriers, that means I could have thermal transport where carriers are simply phonons. Okay, so for example, I have a bunch of oscillators and I have the phonon bars, and let's say they're all coupled by oscillators, but this is a fully quadratic Hamiltonian, and this is again non-interacting. So you can write down your current and fluctuation. And if you look at this R1, again, what you can show is that this is always positive. Okay, so so that means independent of whether it's a Markovian dynamics, non-Markovian dynamics, somehow this bosonic statistics. So you see here, once again, you have transmission and you have purely bosonic statistics because you have boson bars, you have phonon bars. This is always true. On the other hand, a minimalistic version of or a different version of this, different model that you can think of, which have a hybrid statistics. Is a famous spin boson model. So you have just a 2-level system, which is a qubit coupled to phonon bars. And in that case, the reason I call this is a hybrid, so this is kind of hybrid statistics that is going on. Again, very intuitively, why? Because I have the phonon bars, I have a thermal transport happening. So phonon bars give me these Bose factors. That's great. But a 2-level system is much more like a fermion, in a sense that you have just 2 levels, like occupied, unoccupied. So again, this is not a very strong claim, but this is just an intuition that you have. So what you see is that more or less the expressions remain same, except that there is this crucial sign difference. Okay, and that reflects this hybrid statistics. Okay, so you have both distribution, but you get a minus sign, and this once again can give you a notion of deviation from the standard GUR. And whereas if you just purely consider only metals, you have electron transport, now you see again you get a negative sign, but now you get Fermi functions. So again, this can also show violations. Okay, so yeah, so this is a hybrid example. This is a carrier of the transport. Now, depending on the statistics, so the role of the statistics are getting played, and the structure of the junction getting played in these signs. So they have all very equivalent looking forms, but nicely is the appearance of Fermi and Bose functions with plus and minus gives rise to either the bound is lower or tighter. And so this is one result where for the spin boson, because I already showed you what happens for electron case, for the spin boson, there is a violation, and you can show that this violation, it was very hard for us to see the violation, but apparently what we found is that if your bars have some cutoff in the frequencies, sharp cutoff, that's where you can start to see the violation for the standard GUR. Okay, so it does, it does depend on, so the violation does depend on also the statistics of the underlying carriers. And in fact, one of the most interesting results that we found is that as long as you have the bosonic statistics, which in particular for this non-interacting case, where it's all bosonic statistics that is going on, we found that this is valid no matter what you do with the system. So that means it's need not to be only linear response or quadratic response. It can be anywhere. So let's just through this slide, let's just go through very simply how this proof emerges. This is one slide where I show you the proof. So you have non-interacting setup, you have phonon transport or thermal transport going on, and once again you can write the current, which is Landauer-like formula that is well known to many of us, and you have the current fluctuation. Again, these are exact expressions. Now I want your attention here is that if you remember the charge current formula, and if you look at the thermal current due to the phonons, you have a crucial plus sign. So if you look at the thermal current, if you look at the electric current, there was a crucial mark. And other than Fermi functions, of course, there were Fermi functions, but there was a crucial negative sign. But here, for the boson transport, it's a plus sign that appears, and that essentially tells you that this is completely positive, right? Both the contributions are positive, and that immediately tells you that you can use some inequality. So what you do is that you just disregard this term and say that this is greater than equal. Why? Because you want to relate this to the current, and current just depends on transmission. So one intuition is that you can get rid of this.
It seems we have lost the speaker. Let's hold on for a few more.
And that immediately gives rise to the TUR. So what I'm showing in the
Bijay, we lost you for a few seconds there.
Oh, sorry. So can you hear me now?
Yes, we can.
Okay. So what I just said is that I have the current and I have the fluctuation, and for the thermal current where the carriers are phonons, there is a crucial sign difference that appears in contrast to the electronic part. There was a negative sign. Now this is again the statistics that plays a role, and because of that, what you can prove is by very simple steps that for such type of problem, the tight coupling, the tighter bound is always respected, no matter whether underlying dynamics is Markovian or non-Markovian. So in summary, what I was trying to say is that the statistics does play a role, the quantum statistics does play a role in validating or invalidating this TUR. So this was our work, but then gradually there are other papers that tries to now find the bounds. So there is a violation, right? So it can go below 2. Now there was a question that how below it can go. So there was a very recent paper, in fact not very recent, last year there was a paper by John Gold's group where they tried to show that that this can go below by a factor of 2. So you can have now greater than equal to 1, and this is a fairly a general situation. So our analysis certainly respects that, but now it's greater than 1. But once again, so this is again, I think Alexei asked this question that how below you can go. So the answer is 1, but again, this is not an exact proof. I mean, this also has certain limitations. I'll be happy to discuss about the limitations, but again, but at least this paper tries to show that, okay, it's need not to be always 2, and whatever we had, our analysis respects that. But that's not it. In fact, so far I talked about only single affinity problems. So you have single current, but then you can you can increase the problem a little bit more, complexity of the problem by having more currents, and then you can define engine and the efficiency.
Okay.
It involves fluctuation, so that's why it's a very nice thing in the field of stochastic thermodynamics.
Yeah, Bijay, sorry, we lost you again. I mean, for a few seconds.
Oh,
there.
I'm so sorry. I'm connected to Ethernet, but okay. So how about the last slide? It was okay.
Yeah, I mean, on this slide, sorry, we lost you.
Okay. So in this slide, what I'm trying to point out is that it's not only the at the level of current that you can investigate TUR, but if you have multi-affinity problem where you support multiple currents, you can define efficiency. And then this efficiency can involve bound in terms of fluctuations. So what I pointed out is that typically, there are bounds that we know at the level of only means or averages, but now because of the TUR, there are various bounds that are extended which involves fluctuations. So that's why it's very interesting in the field of stochastic thermodynamics. Okay, so this is the theoretical part. I guess okay, Juza, how much time do I have?
You're more or less out of time.
I'm more or less out of time. So I think I won't be able to get into the experimental part. Okay, so this was, yeah, I think Juza told me that I should not prepare too many slides. So, okay, so maybe I just flash. Give me Juza 2 to 3 minutes. I'll just flash the results. Is that okay?
Surely, surely.
Okay, so all I'm going to just flash you, and so we collaborated with 2 experimental groups to essentially understand experimentally or see experimentally, the validity of, understand the validity of this relation. So one experiment that we did in the steady state. So far what we discussed in the steady state TUR experimentally, we collaborated with Oriental's group. So here they could do experiment in atomic junction where they have, they can measure both current and fluctuations, and they could basically analyze. So we took their data and we started analyzing the TUR. So again, here it's a Q minus 2. So if it is greater than 0, you have the tight bound. So what we observe is that that this is always respected. So here we didn't find any violation. There are multiple reasons for that. One of the, because of the parameter regime, that's number one. Where they worked, the parameter regime was far off from where you actually see the violation. And also there was in this junction, most cases, the transmission was kind of constant. So constant transmission, as I mentioned to you before, that the TUR is kind of always there. So so this was a paper where we see the validity at least. Hello, Juza, can you hear me?
Yes.
Okay. Okay. Yeah. All right. So this was a steady state paper, but then we also investigate what happens to these uncertainty bounds in the transient. So now there are a lot of activity of extending this relation, not in the steady state, but in the transient. So when I say transient, what I mean, you basically consider 2 systems which are at different temperatures, and then you suddenly connect them. So there will be heat flow, there will be fluctuation of heat, and there will be entropy production. Now, it's not a rate, but it's a total entropy production. And the similar question that one asks is, what happens? Is this bound gets respected? And this is what we in fact experimentally did both theory and experiment. And experiment, we essentially do NMR. I'm sorry, I'm skipping the slide, but I just want to show you that what we essentially do is that we realize a molecule where essentially we have 2 qubits and we initialize them at different temperatures, and then we measure we essentially do tomography. So you basically have 2 qubits tomography where you get the entire density matrix, and what you can perform some calculation and show that the current and the heat and its fluctuation, you can just get all of it just from the density matrix of the 2 qubit problem. If you do that, so this is the result of the tomography. But if you do that, you essentially can now uncover like what regime you can start seeing the violation. And let me tell you that there is a regime again, at least for this plot, you see that there is this violation. You have this TUR. If it is negative, there is a violation. You precisely see that there is a regime where there is a violation. And in fact, this violation, once again, even in the transient, you see that if the third cumulant is negative, which is the third cumulant is this black line. So when it's negative, you have a violation. So this is now experimentally confirmed. And you also get under what value of the coupling, because you have 2 systems and you're coupling it, right? So there is some coupling value when you start to see the violation, and one can also understand this. Just to end this, we have a follow-up theoretical paper for the transient also. And I just want to end with this, that again, we ask the same question in the transient, how the statistics matters. And interestingly, what we found is that if you have just 2 spins coupled and you construct the TUR ratio, you have this, there's a minus sign. And that essentially tells you that there is a violation. And this is a plot where you see that these blue ones are essentially the regimes where you see violations. And overall, in a broad regime, this bound gets respected. Whereas you can think of other problem, which is instead of 2 qubits, you take 2 oscillators, harmonic oscillators, and couple them. Again, there is a statistic point, and you will very nicely in this very simple calculation, you can show instead of minus, now you get a plus sign. Just because these are harmonic oscillators, and very nicely, again, harmonic oscillator somehow is very robust, even in the transient, it always respects, it never goes down. But on the other hand, so I
Yeah, I'm sorry, we seem to
kind
be
of flash
having
through
these
the
connection. Bijay, we seem to be having connection issues again.
okay, I'm
Sorry,
yeah.
we just missed the last part on the
Yeah, so the last part,
oscillator.
so the harmonic oscillator, as what I was saying is that this ratio, if you instead of 2 spins, couple spin, if you take 2 oscillators, you now get, this is an exact result, you get a plus sign instead of a minus, and it becomes greater than 2. So what I'm saying is that for somehow harmonic oscillator system always respects the 2, even in the transient and as well as in the steady state. And this has, again, as I said, I don't have a concrete evidence, but maybe the dimensionality also plays a role, that this is kind of infinite channels that you have, in contrast for the coupled spin that have finite size Hilbert space. So I have to apologize again, because I rushed through this part, and I just sort of just show you some of the slides, but with that, I think let me just tell you that there are now loose bounds that people have found in this direction, and these are the 2 very important papers where they essentially have the answer to the question that we started asking, is that how from the fluctuation relations you can get these bounds. And what they found is that there are loose bounds, and they have quantified. So these papers are now in this direction, and of course we always respect these bounds. There are no violations to this. So with that, I think I'll just summarize, and so all I want to say is that, of course, Jose, can you hear me?
Yes, we can.
Yeah.
Yes.
So in summary, of course, as long as you have, small systems where fluctuations do play a very role. So it's very important that, we look at not only mean and averages, and now this is one quantity, one bound that involves both the current and fluctuation in terms of entropy production. So this is the thermodynamic uncertainty relation. And what I try to point out is that the one that was proposed for Markovian system, that's not general one. Of course, you have situations where they can get violated, and one of the reason of investigating those is that other than, of course, there are now universal bounds that I showed you in the previous slide, starting from fluctuation symmetry. Now, this was one of the questions, that when something is very universal, they don't reveal much information. They don't reveal what dynamics is happening, what is going on with the system. But somehow this tighter bound gives you an understanding about the underlying transport processes. And what we show is that, at least for quantum system, by taking into account certain quantum effects, how these violations can be achieved. And something that I didn't mention, but now we have experimental sort of work where we assess the validity of these relations in various setups. So for the transient case, we looked at the NMR setup, and in the steady state it was the atomic junction. So with that, I want to summarize, and I want to thank my collaborators, and Mahesh, who is a experimentalist who runs NMR lab in ISER Pune, our long-term collaboration with Divya Segal. I have to thank Warren Talanofi for the atomic junction work, and as well as my students who have done a lot of this work. So with that, I want to thank you, and I have to once again apologize for the last part, which I just ran over very quickly. Thanks.
So thanks a lot, Bijay, for this wonderful talk. Let's see whether this works.
Oh, wow, this is nice. Thank you.
Yes, and I think we also have a discussion session after this. So
That's
I think if people are interested in the experimental part, we can always ask you questions in the discussion session.
For sure. I'll be more than happy.
Let's take a few questions from the audience, if there are any.
Sure.
Alexia, please go ahead.
Yeah, I have a couple of simple questions regarding the statistics.
Yes, please go ahead.
So when you were mentioning, so the impression I'm getting is that bosons, it's very hard. Well, essentially, you didn't find any examples where bosons were violating.
Very nice. Absolutely, yes. True.
So the example where you considered phonons, I'm still curious whether the result that you showed, were you considering translationally invariant system, so phonons generated in a translationally invariant system, or it doesn't really matter whether there's translation invariance?
No, no. All it matters, Alex, is that it's no. So there is no thing about whether there is a translation invariance in this or not. I mean, that will only tell you whether you have omega equal to 0 mode or not. So, but you can have oscillators which are pinned and so on and so forth. As long as theoretically speaking, this is fully quadratic. You have these expressions. The only thing that you want to change is the shape of the transmission, but what we show, as long as they follow these bosonic statistics, it's just going to be always respected. But
okay, so
yeah,
then a nasty question. So then what happens if you look at anyons which are neither bosons
okay,
or...
so that's another interesting question. I don't know. That's a wonderful point, and something that I'm learning by myself now. And what happens to anion? That exactly was another question. I don't know. I absolutely have no idea. I'm not an expert in that, but that's certainly a valid question. But what I can tell you, and what my intuition again is that, I mean, when you have this harmonic oscillator, but now think about putting anharmonic interactions. Think of like a both Harvard kind of model where you now start putting the on-site interactions or this nonlinear interactions, and that is essentially going to suppress the size of the Hilbert space, right? And you can essentially go deep down to two-level systems. And that's where we see violations. So somehow, for example, here, the spin boson is nothing but you have a single oscillator and put a high nonlinear interaction. So instead of having infinite levels, you just bring to a two-level problem. And we start to see the violation. So that's just a side comment, but you are absolutely right. I mean, I don't have an answer to what happens. So we just looked at Fermi and Bohr statistics problems, but anion statistics certainly is an open question, and I'll be happy to discuss more with you. So there was a very recent paper, not in this direction, where I'm trying to learn about anion problems, but yeah, it's gonna take quite a bit of time for me to absorb that.
Okay, yeah, thanks.
Thanks, Alexi, for this wonderful question.
Let me just quickly ask you one question, Bijay.
Sure,
so you also mentioned that there are these tighter bounds, on
not tighter, but looser.
Oh, sorry, looser bounds. And yeah, there was one result that you mentioned that it is greater than equal to 1 also, right?
Oh, yes.
And but of course, based on your talk, it seems that this has to depend again on the statistics, right?
Very good. No. So
what is happening here? Because you say that your bosons, right, the lowest bound would always be 2, basically.
So if that is respected, this is always getting respected, right?
Surely. But then it's, yeah.
So what I'm saying is that this is a fairly general result, which is independent of any statistics, as far as I remember the proof, because they use some geometry, quantum information argument to, particularly this Kramers-Rao bound kind. So this inequality arises from this Kramers-Rao bound kind of picture where they incorporate Fisher information, and there is no statistics that really gets into this. So I pretty much believe that this is always true, but again, there is one strong limitation. The limitation is the following. This is not to all orders of the affinity. So this is, you can, this is probably like second order or fourth order of the affinity. So this I don't remember exactly, but this is again not an exact result. But certainly if I have the tighter bound, which is greater than equal to 2, I certainly respect this. And in all our work, wherever we have seen the violations, which is lower than 2, of course we respect this. And this is, in fact, this paper actually showed taking our sort of setup and actually validate that, oh, okay, whatever we have observed certainly respects it. So they have done that job very nicely.
Yeah. Okay. And sorry, one more quick question would be,
please,
that you were mentioning this as a passing comment to Alexei. You started with a 2-level system, but you could increase the number of levels, right?
Right. True,
I mean,
true,
and you could just keep adding more and more
yes,
levels
yes,
to this two-level system.
yes.
Then the question is, at how many levels do you?
Yes,
So let's
yes.
assume you are in the regime where TUR is violated.
Right.
How many levels do you need
Right.
to get TUR again?
So that's again a very good question. We didn't do it so basically you do an n level problem, and you basically look at what happens to TUR as a function
of n.
Yes,
exactly.
we didn't do it, but I would request you to look at this paper that I again this paper, I just sort of mentioned these two examples in this latest paper. Here another thing that we did, one of the problem that you can think of out of these two is again a hybrid problem where you have a oscillator and a two level. Right, I mean you have two level, you have two oscillator, but then you have one oscillator and a two level. So that's like a James Cumming model in quantum optics, right? And again, so there also we see that there is a violation. So my rough intuition is that as long as maybe not. I mean, somehow it has to do with the finite size of the space. So as a function of n, it's a very good question that to what n you will. So let's say you start with n equal to 2, you have a violation, and then what n it will stop showing the violation. I don't have an answer. All I know is that at the limit n tends to infinite, certainly there won't be any violation, but for finite n, that's actually a very good question, and I don't have an answer to that.
All right. If there don't seem to be any more raised hands from the audience, so if there are no more questions, let's thank our speaker once again.
Thank you everyone for attending the talk.
And, I suggest that we take a little 5-minute break and come back after 5 minutes. I'll keep this session open. So we just come back after 5 minutes for a more focused discussion. But
okay, so I'll be online. So okay, so I'll be